The parallel AC circuit is shown here, uh, and the power supply or the voltage source is connected in parallel with each of the components. You'll notice that there is a phase angle. This is not something unique to the parallel circuit. I just put that in there for the fun of it. And the currents have been defined for us in the directions. So IT, the total current, is coming out of the source, and I1, I2, and I3 are going through the devices, and so this will match everything. Now we could do this using Kirchhoff's voltage law and Kirchhoff's current law, but we'll just look at it from a simple matter just to get used to playing with complex numbers. So we see that we have our polarities plus minus, plus on the top, minus on the bottom for all of our devices or parts. And our frequency is 350 hertz. Our voltage V1 in phasor form, well, we need the RMS value for the amplitude, so that's going to be 2 volts over the square root of 2, and the angle is just going to be the 30 degrees. R is 15 ohms. C1 is 15 microfarads, and L1 is equal to 10 millihenries. So let's calculate our capacitive reactance, and that's just equal to negative J over 2 pi frequency times C1. So that's negative J over 2 pi times 350 hertz times 15 microfarads. And that gives me a reactance of negative 30.315 J ohms. For my inductive reactance, that's just going to be J 2 pi frequency times L1. That's J 2 pi 350 hertz times 10 millihenry, and that equals 21.991 J ohms. And we can calculate our total impedance, which is ZT, and that's going to be equal to, well, I could write this as 1 over ZT is equal to 1 over R1 plus 1 over XC, my capacitive reactance, plus 1 over XL, which is my inductive reactance. And if I calculate for ZT, I get 14.492 plus 2.714 J ohms. So now we can start looking at the current that is flowing from the power source, the voltage source V1, and that'll be our starting point for the next video.